All right, thanks for staying for the last talk. This talk's going to be given by Kevin Thompson, and he's going to tell us about an application of the level-2 quantum Lasserre hierarchy in quantum approximation algorithms.
Hello? Okay. Today I'm going to be talking about an approximation algorithm that makes use of the level-2 Lasserre hierarchy. And sort of the moral of this story is how cool of a tool the level-2 quantum Lasserre hierarchy is. So here's the problem. It's called quantum max cut. It's just kind of the anti-ferromagnetic Heisenberg model. I just want to get this notation out of the way. So sigma I for sigma one of these Pauli matrices, I just mean to put Pauli sigma on qubit I, and put identity on the rest. Okay, so quantum max cut is just sort of given the interaction graph, what's the energy of the anti-ferromagnetic Heisenberg model. So given one of these graphs, put a singlet on each edge and then tensor it with identities on the rest, and you kind of sum up all of those, and then just tell me what the largest energy is. The model is really important for all kinds of physics that people care about. I really might not need an introduction, but it's QMA hard to figure out what this energy is, so our only hope is to try to approximate it. So what do I mean by approximation? There's a lot of different natural things I could mean. What I mean is a classical algorithm that takes as input the description of the Hamiltonian, or in this case, the graph, and outputs a classical description of a good quantum state for that graph. The performance guarantee is that no matter what instance I give it, I know for sure that I'm going to get objective at least fraction alpha of the optimal objective. And normal stuff, it runs in polynomial time and n the number of qubits. Unlike the classical kind of combinatorial optimization case, there's this kind of interesting question in the quantum case, which is what sort of classical description should we use? You can't represent an arbitrary quantum state on a classical computer, so this is kind of a design choice in your algorithm. There's two ansatz we're going to be interested in. One is the product state ansatz, where you just kind of have tensor product of local qubit states, and the other one's going to be singlets and product states. Okay, so I just wanted to give you a picture of like what rounding normally looks like. So for classical combinatorial optimization, the problems are hard because the domain is really hard to optimize over. In that case, it's an exponentially large set of discrete points. So what we do is we relax this region to like an easier region to optimize over, but that kind of contains all of the feasible points. We find kind of the best possible point in this relaxed region, and then we have some procedure called the rounding algorithm, which takes this infeasible point and maps it to a feasible point. The thing we have to do is bound the loss and objective that procedure took. The quantum picture is actually kind of the same. So the n qubit space, we can't really optimize over that in the classical computer, but there are kind of unphysical sets of states that we can optimize over on a classical computer. So the idea is find the best unphysical state. This is kind of the thing with a nice classical description, and then use that to construct a qubit state, and kind of the same thing, worry about how much objective loss you took. So this is all the previous work on this problem. It's, there's been a lot of pretty recent work on it. There's a few things I want you to note. One is that pretty much everything is a product state algorithm. There's only a handful that are kind of the singlet plus product state ansatz. There's no upper bounds because, we don't know any quantum version of the PCP theorem. And another thing I want you to note is that all of the product state algorithms seem to be mysteriously bounded by a half. This alpha seems to be bounded by a half. There's a really simple reason for that. It's just that your approximation factor has to hold uniformly over all instances. And for a single edge, the best you can hope for is a half, because for a single edge, the best product state has objective a half, but the best quantum state has objective 1. There's a lot of evidence, though, from this Anchugasa-Morenz and others, that kind of small graphs are sort of blocking getting a good approximation factor on these instances. So they give a 0.546 algorithm that gives the product state algorithm, but it beats a half if the graph is large enough. There's kind of a lot of results actually in this. So there's a very well-known Brandau-Hauer paper from 2016 where they say that for dense graphs, the optimal state is very close to a product state. So it's kind of reasonable to expect that if you have an algorithm which gets a good approximation factor, it's got to look like a product state algorithm in the regime of dense G. And indeed, the kind of main result of this AGM paper is approximation factor better than a half by kind of trading off between a product state and a product state plus singlet ansatz. So if we find better product state algorithms, we can actually improve the performance of non-product state algorithms. But the kind of entangled ansatz, that's kind of the frontier, and we're going to talk about sort of one of each. So I'll be talking about 2 papers. One's on the archive, and one should be out there shortly. We kind of shave tiny bits off of the state-of-the-art approximation factors. So like I said, the really cool thing is the techniques we use. So the first one is a kind of 0.533 approximation that kind of uses an entangled ansatz. And then this new one, which is going to be on the archive soon, is a kind of an optimal product state algorithm for QMC. So we get a polynomial time classical algorithm that gets exactly factor a half using the product state ansatz. As usual, we should kind of be careful with disclaimers. I'm not saying that I'm getting the optimal product state for every instance. I'm just saying overall, I have the best possible approximation factor. And we also have sort of a kind of a fine-tuned version of Brandau-Hauer. So if the graph has min degree D, where D is kind of doesn't even really have to be that big, we kind of beat a half pretty handily. Okay, so I'm going to tell you about the Lasserre hierarchy, but to kind of move there, I have to tell you what a moment matrix is. So given some state psi, just construct this matrix V, where every row is just psi acting on one of the distinct Pauli matrices. And then you consider this moment matrix M, which is just V times its dagger. There's a couple properties I want you to note. It's kind of a very redundant description of all the Pauli expectations. So in any row or any column, I should see any Pauli expectation that I want to know about. And it's also obviously PSD because it's kind of defined by its Cholesky decomposition. Okay, so we can imagine thinking about a moment matrix and kind of being hopeless because how are we going to optimize over this gigantic thing? And one thing you might think to do is to kind of optimize over a submatrix of this and sort of ignore the rest. So you optimize over, you have like one of these little guys be a variable in your optimization, and you kind of just don't worry about enforcing anything else beyond these boxes. You could still assume some pretty nice constraints. So you could assume that each of these matrices is PSD, and you can also assume any like equality constraint that overlaps with the submatrix you're considering. And then kind of Lasserre 1 and Lasserre 2 are very easily defined then, or just kind of Lasserre 1 is the submatrix corresponding to 0 local and 1 local Pauli terms, and Lasserre 2, you go from 2 local down to 0. So this, I can tell you what this kind of non-physical space of density matrices is now. This is just kind of a set of operators in the Pauli basis where kind of Pauli expectations are defined using one of these submatrices. So what you're going to get when you when you get one of these things, you'll have a matrix which is not PSD, but it sort of respects kind of things you would expect from a low order submatrix of this giant matrix. Okay, so the next question is, what's the difference between the levels? What is going to Lasserre 2 really buy you? So you could imagine testing it with sort of an example graph. You could write a graph down and say, how do these two things compare? And the optimal quantum energy is well known since the 60s. It's just if there's Q edges in the star graph, then it's Q plus 1 over 2. I like to think about this sort of as like a monogamy of entanglement inequality, because it's sort of like saying if on this edge I have objective 1, then on this edge, obviously my objective is kind of bounded by a half if there's only 2 edges in my star. And it turns out Lasserre 1 is really bad at respecting this inequality. So Lasserre 1 would tell you that you can have a state which is maximally overlapping with 2 overlapping singlets, which violates monogamy, whereas Lasserre 2 actually gets the right answer on this graph. And so that was kind of a relatively simple bound. It worked for our first entangled rounding paper. But as you expect, this is kind of a simple inequality. We're not really fully capturing what a quantum state is. In particular, you can look at this and you can see that, well, if I set one of the overlaps to be 1, this thing forces the adjacent overlap to be a half. But monogamy actually says that if one of these overlaps is 1, then kind of the third qubit must be totally unentangled with qubits 0 and 1. So you'd actually expect objective exactly a quarter there. So we demonstrate in the second paper this stronger thing we call the triangle bound, which is if I have overlaps defined from one of these Lasserre 2 pseudo-densities, then they satisfy these inequalities on the right. I mostly wrote them down just so you could see that they're not too complicated. And you can check by plotting these that these do kind of respect the nice monogamy thing I was talking about before. So if you force mu01 to be 1, then mu02 does indeed, it forces it to be a quarter. And then we're pretty sure that these constraints are actually sort of fully capturing the allowed values for a legitimate quantum state on a triangle. Okay, so I'm going to tell you about the rounding algorithm now. Both papers use the same kind of meta algorithm with kind of interchangeable building blocks. The idea is, we know Lasserre 2 is a good relaxation, so maybe we should listen to what it's telling us. Lasserre 2 is giving us these values mu for every pair, every qubit pair. And it's saying that if mu is close to 1 for that edge, then it really thinks that edge should be a singlet. So this overall strategy is just to kind of take that advice into account and to actually sort of put singlets or something as close as possible to singlets on the edges that Lasserre thinks should be singlets. So the kind of formal thing is you construct this set L, you set some threshold, and you put all of the edges into L, which are above some fixed threshold. L is like a subgraph of the overall graph, so you find a maximum matching on it. And then, you worry about 2 different states. So one state, you do kind of something optimal on M. It's a matching, so it's really easy to optimize. You do something standard on the rest. And the other state is you kind of do Parekh rounding on that, and you take whichever state has better objective. Okay, so why do I need different blocks? Well, one's product state and one's entangled state. But really, so the threshold sets kind of the degree of the graph L you get out. So if the threshold is very high, then that means like large edges would be kind of adjacent to no edges. You'd get a degree 1 graph in L just by the bound. Whereas if you kind of have some intermediate value, the degree of the graph you get might be 2 or 3. The real reason we need kind of different thresholds is pretty technical. So I'm just going to say that if D is kind of too small, then the product state algorithm is bad, whereas if D is too large, then sort of the matching state is bad. And so the other interchangeable block is what we actually do with the matching. So this like the state that we're constructing and then comparing to the standard state. So for the entangled rounding algorithm, we're just going to put singlets there. I mean, that makes sense. We're trying to maximize overlap with the singlets. We're going to put maximally mixed states on these guys. Whereas for the product state rounding, we're going to put some specially chosen state, which gets objective exactly a half on the matching. And we're going to do GP rounding on the remaining qubits. OK. The analysis is actually pretty easy to describe. So there's 3 kinds of edges you have to worry about. Edges in M, edges immediately adjacent to edges in M, and edges that are kind of far away from M. Edges in M, that's easy. We've kind of purposefully designed our algorithm to get good objective on those edges. Edges kind of far away from M, those are also not too bad, because in the entangled case, you're looking at the maximally mixed state, whereas in the product state rounding, you're looking at the performance of GP rounding, which is very well understood. The thing we kind of have to worry about are the edges that are immediately adjacent to edges in M. And this is where the triangle star bounds come in. So the way the rounding algorithm works, it sort of forces half of these edges. So we kind of don't have much control over the objective we get on it. But the point of the triangle star bounds is that edges close to large edges must be small. So the SDP must not be doing very well on these edges either. So we're kind of OK with not doing as well on them ourselves to get a good approximation factor. OK, so what are the implications? We've demonstrated that Lasserre 2 satisfies some really cool monogamy of entanglement constraints. I like to think about it as you've kind of shown that this low order or sort of quasi description of a quantum state can still look entangled. We've also, another important thing is we've kind of brought the standard classical recipe into this entangled rounding picture. So there's a lot of classical results which make use of the higher levels of Lasserre hierarchy. And so by showing how to do this, maybe we can bring in those results and have implications for quantum rounding algorithms. Another thing we do in the product state rounding paper is we have pretty strong computational evidence that the rounding algorithm is also optimal for rank 1 projectors, but we couldn't quite prove it in time for the deadline. The open questions here are, I think Lasserre 2 might even be cooler than I already think it to be. So there's these questions of like, what kind of graphs is Lasserre 2 exact on? Oops. And what kind of other monogamy of entanglement constraints can we find? More generally, what sort of things can we expect from K as order 1? And then the other kind of big question is, singlets and product states are still locally entangled. It's still the tensor product of local states. So can we get something really, really entangled, like maybe a tensor network state or something? And then sort of looking for genuinely quantum approximation algorithms, something actually kind of making use of a quantum computer to approximate. I'll just do a quick plug. We're hiring a postdoc. According to Ojas, this link may or may not work, so just come find me. I'll give you my email. Thank you.
All right, we have some time for questions.
Hi, thanks for the talk. So you asked, one of your open questions had to do with using Lasserre K and rounding from that. So, I mean, is there a systematic way you can think about generalizing what you do with Lasserre 2 and rounding to, single qubit and 2 qubit states? Can you imagine generalizing that to Lasserre K and rounding to, product states where the tensor product factors are K qubit states?
Yeah, so we've sort of thought about, so that's kind of like a different ansatz. We did think about that, and we ran into the problem that like the geometry of the block sphere for even 4 qubits is crazy. We couldn't really come up with anything. So that like when you try to round to that, you're almost always going to get something very close to the maximally mixed state. It's hard to see kind of what the right thing to do is, but it's an interesting question for sure.
Thanks.
This is maybe not a very interesting question, but I didn't think I fully understood like the steps that were taking place in sort of the protocol that you were describing. To construct these sort of Lasserre numbers, you need an input state. Is the input state is sort of like not a real quantum state? It's sort of
No,
like
so the Lasserre only takes as input the description of the Hamiltonian. So just this graph G.
Oh,
And then
okay. I
it
didn't
solves a
understand that.
classical semi-definite program to get you these mu values.
Oh, okay.
And then you use those to kind of,
I see. Okay, thank
Go
you. That
through it.
helps.
Hi, yeah, I was wondering if you have a conjecture about, should there be a separation between the approximation ratio that you get with tensor networks? You mentioned tensor networks in your open problems versus these kind of locally entangled types of approximations that you're doing.
yeah, I don't know if we know. It's just really hard to like contract tensor network states formally. So I wouldn't venture a conjecture. Yeah.
Thanks.
Yes, usually Lasserre hierarchy, you don't have any bound on the dimension of the operators, but here it's the case, right? So what, like, can you use it? Do you use it or?
Yeah, so the thing you're talking about is equivalent to this kind of moment matrix thing where, yeah. So you're talking about the hierarchy where you have kind of like equalities and inequalities on your linear operators and you optimize over that.
Yeah, if you want the maximal violation of a Bell
Yeah.
inequality, for instance.
Yeah. So sort of for like just kind of restricting yourself to small semi-definite programs with that hierarchy, this thing is what you get, this Lasserre thing. So this isn't, I'm not optimizing now over kind of arbitrary dimension things. I'm just saying, this is a PSD matrix. This is a variable. Let's just optimize over this guy.
Yes, so, but here you are not using the fact that X1 is of fixed dimension, right? So you would do the same even if X1 was of any dimension. So here somehow you have more information about X1.
Yeah, that's
which
true.
you are not using.
Yeah, yeah.
But okay, you don't use.
I'm not sure how to use that.
Okay.
Yeah. You are using n, right? Because the size of this matrix is like n choose 2 plus.
Yes, yes.
Yeah.
But in standard Lasserre, you do exactly the same then.
Yeah.
Okay.